Hello everyone, welcome back to Mtari TV. My name is Robert Mtari and I'll be your pure physics tutor. Alright, so in today's topic, you're going to learn the topic current electricity. Then at the end of the topic, you're going to have an exam practice where we answer a question in the past paper on the same topic we're going to learn so that we can solidify our understanding. The best way to study is to learn, then apply what you have understood. If you're able to apply what you have understood in this, that you're going to understand in this video, then our work is done. All right, so let's start. So before we go into the concepts, it helps to know that every electrical circuit is drawn using what? Standard symbols. Things like a cell, a resistor, a bulb, a switch, ammeter, voltmeter, all those things are drawn to what? A standard drawing. So being able to recognize these symbols correctly and quickly is the foundation for reading any circuit diagram. Alright, so let's begin with the electric current itself. So current is the rate of flow of charge, and this is represented by the symbol capital letter I, and its SI unit is ampere. The formula is equals to I is equals to capital letter Q divided by small letter t, where Q is the charge measured in coulombs and T is the time measured in what? In seconds. So when we use an electrical appliance, current flows through the circuit. And this simply means that electrons are flowing throughout that circuit. Current is measured using an instrument called the ammeter. And this ammeter must always be connected in series with the component you are measuring. So never forget that. An ammeter must always be connected in what? In series. It also has a positive terminal, usually colored red, which must be connected to the positive terminal of the battery. And it also has a negative terminal, which is usually black, which connects to the negative terminal of the battery. Alright, so now let's focus on what we call the electromotive force, usually written as EMF. So by definition, this simply the energy supplied by a cell or a battery to each column of a charge that passes through it. And its SI unit is the voltage. So the formula is EMF is equals to capital letter D divided by Q, and where E is the energy supplied by the cell in joules and Q is the charge in coulombs. It's worth remembering that 1 volt is equal to 1 joule per coulomb. Alright, so the other thing which is similar to EMF is what we call the potential difference, or PD, which is the energy. By definition, potential difference is the energy converted by unit charge as it passes through a component in the circuit. It's also measured in in volts. So the formula is voltage is equals to capital letter E divided by capital letter Q, where E is the energy converted to other forms within that specific component, and Q is the charge flowing through it. So the potential difference is measured using a voltmeter, and unlike the ammeter, the voltmeter must be connected across a component in parallel. Please always remember that, in parallel. Each time you're connecting a voltmeter, it must be connected into a parallel direction and not in series. So the same rule about the terminals is the same thing about the voltmeter. The red one is to the positive and the black one to the negative. It helps to think of it this way. Energy from the cell is carried by the charge and then used up as it passes through the components like resistor, bulbs, and heaters, converted into forms like light or heat. And that used up energy per unit charge is what we call the potential difference across that component. Now let's talk about the electrical resistance. Resistance. So resistance is the opposition a circuit offers to the flow of current. As a definition, represented by the symbol R with the SI unit ohm. The formula for resistance is equals to capital letter R is equals to V divided by I. And this relationship is known as the Ohm's law. So Ohm's law says that the current passing through a conductor is directly proportional to the voltage across it, provided that the temperature remains constant. So some components such as the bulb and heaters naturally have resistance, and any device built specifically to provide resistance in a circuit is called a resistor. A specific type of resistor whose resistance can be adjusted is called a what? A rosette. If you have a plot, a graph of voltage against current for a conductor that obeys Ohm's law, you get a straight line passing through the origin, and the slope of that line gives you what? The resistance. There are conditions that must be met for Ohm's law to be what? To be held. So the temperature of the conductor must remain what? Constant. Because an increase in temperature increases what? Resistance. The conductor must not be under any mechanical strain, such as being stretched or bent, since the length of the conductor affects its what? Resistance, and the conductor should not be placed at right angles to a strong magnetic what? Field. A conductor that obeys Ohm's law under this condition is called an ohmic what? Conductor. So a conductor that obeys Ohm's law under this condition is called what? An ohmic what? Conductor. While one that does not is called what? A non-ohmic what? Conductor. So with resistors understood, let's look at how resistors behave when they are arranged differently in a circuit. Starting with resistors in series. So in a series arrangement, the current is the same at every point in the circuit. So current is equals to current 1. Current 1 is equals to current what? 2. So the sum of the potential difference across each resistor equals to the total EMF of the source. So EMF is equals to the first voltage plus the second voltage give us what? Voltage. And the total resistance of the resistors connected in series is simply the sum of their individual what? Resistance. So resistance is equals to R1 plus R2. Alright. Now let's see compare that with resistance in what? In parallel. So in a parallel arrangement, the total current in the main circuit is the sum of the currents flowing through each separate branch. So current is equals to current 1 plus current 2. So every resistor arranged in parallel has the same potential difference across it, equal to the same EMF of the source. So voltage is equals to voltage 1 is equals to voltage 2 as well. So it's the same throughout that circuit. So instead of simply adding resistance, the reciprocal or the total resistance equals to the sum of the reciprocals of the individual resistance. So 1 divided by R is equals to 1 divided by R1 plus 1 divided by R2. When there are only two resistors in parallel, there is a short formula which is equals to resistance is equals to R1 times R2 divided by R1 plus R2. Only when there are only two resistors in what? In parallel. That's when you use this formula. But if not, you use that one with we started at first with 1 divided by R is equals to 1 divided by R1 plus 1 divided by R2. But if you are dealing with just two resistors in a circuit, you can use the last formula, which is R is equals to R1 times R2 divided by R1 plus R2. Alright. Sometimes the circuit combines both series and parallel arrangement at once. So in such cases, you first work out the effective resistance of the resistors in what? In parallel, and then add the effective resistance to whichever resistors are in series with it to get the total resistance of the whole circuit. Alright, now let's move on to electrical power. So electrical power is simply the rate of using electrical energy represented by the symbol P measured in watts. The formula is P is equals to voltage times current, where V is a potential difference and I is what? It's a current. So power can be expressed as P is equals to E divided by T, which rearranges to E is equals to VIT. So a 60-watt bulb, for example, converts 60 joules of electrical energy into light and heat every second. Alright, so now that we have understood power, we can look at how the cost of electrical energy is calculated in the home. So electricity meters measure energy in kilowatts hours, and 1 kilowatt hour is called 1 unit. So to calculate the cost of electrical energy, you first calculate the energy consumed using E is equals to PT, where power is in kilowatts and time is in what? In hours. Then you calculate the cost by relating the number of units used to the price charged per unit. Now let's look at how electricity is actually used safely in the house. So when an appliance is plugged into a circuit, it connects through a system of wires. And in Zambia, this is done using a 3-pin plug. So the live wire is brown, and its function is supplies electrical energy to the appliance at high voltage, making it dangerous to touch since current would flow through your body. So the natural wire is blue, and its function, it completes the circuit for the appliance. Then the earth wire is green or yellow, and its function is simply connected to the metal case of an appliance. If a live wire accidentally touches that metal case, the earth wire gives the current a safe path to escape into the ground instead of passing through the person touching the appliance. So that is the function of the live wire or the earth wire. It's simply to provide a path for the exposed current to go to the earth and not to the person touching the appliance. All right, so with that in mind, let's look at the dangers electricity can present. Contact with electricity, especially the live wire, can cause electric shock, and a large enough current can be fatal. It can also cause fires and burns in appliances, plugs, and circuits. These damages usually come from three situations. The first is damaged insulation, where worn-out insulation exposes the live wire and allows contact that can cause shock or fire. The second is overheating of cables, which happens when too much current flows through a wire or a component, melting the insulation, potentially starting a fire, often as a result of short circuit or overloading. The third is a damp conditions, such as a wet bathroom, where the human body resistance drops significantly when the skin is wet, allowing current to flow through the body far more easily when the skin is dry. And the fuse is designed to prevent too much current from flowing through a component. If current gets too high, a thin wire inside the fuse melts and cuts off the flow before it can cause overheating or fire. Like the switch, the fuse is installed on the live wire. Alright, finally let's look at the fuse rating. So fuse rating is the maximum current a fuse can safely carry without melting. So choosing the correct rating meter, if a fuse rating chosen is too high or too large, it allows too much current to flow before it reacts, defeating its purpose. So if it is too small, the appliance will not even be able to work properly, since the fuse would meet under normal operating current. As a rule, the fuse rating chosen should be just slightly larger than the working current the appliance normally draws under regular And that brings us to the end of the current electricity. I want to answer a question that came in the 2024 Pure Physics Paper 2, Section A, Question 8. Alright, so it reads, Figure 8.1 shows an incomplete circuit with resistors in series. The resistors have values of 6 ohms and 12 ohms, respectively. Question 8a reads, complete figure 8.1 by drawing the symbol for the ammeter and for the battery. Include the voltmeter connected to measure the potential difference across the 12 ohms resistor. Alright, so we have learned that during the lesson, please. We have learned that and the ammeter is always connected in series. The ammeter is always connected in series with the component is measuring. That we have also learned that voltmeter is always connected in parallel to the components it's measuring. Then we also learned the symbols for the electric circuits. That's completely question A is asking for. So we're going to put our A there on the other side where it is there. Then we're going to put our voltmeter below the 12 below the 12 ohms resistor. Why? Because it's parallel in that manner. Then our battery I've already included there. Alright, so we move on to question B, question 8b. So question 8b reads, if an ammeter reading is 0.55 amps, calculate B1, the combined resistance of the two resistors. Alright, so the combined resistance of the two resistors, how do you find it? You simply say total resistance is equals to, you just add the 6 ohms and the 12 ohms, giving us what? 12 ohms resistance. Then number 2, 12b, it reads, calculate the EMF of the battery. Alright, so for us to calculate the EMF of the battery, we're going to use the formula. Voltage is equals to I, which is current, times the resistance, which is R. Now, I've already been told in the question that our current is what? 0.55 amps. And our resistance is what? 18. So just multiply those two numbers. We're going to get your value as 9.9 volts. Alright, we move on to question C. So question C reads, explain how the combined resistance would change, if any, when the two resistors are connected in what? In parallel. So when resistors are connected in parallel, the combined resistance is less than the smallest individual resistance. Therefore, the combined resistance would decrease rather. Alright, thank you for watching the TV. I hope you have learned one or two things. Please do join our online tuitions by WhatsApping us on the number shown on the screen there in one of the following subjects in the following ad. Thank you for watching.